Okay, it's quite hard to be one of the last speaker and say something innovative after all day with so talented speaker bringing their contribution. But I want to open a look, not only on PET, but I want to open a look on polyester and some other aspects. Why it doesn't move? Okay. I don't want to focus too much time on this, but we have not to forget that all the aware that was raised in the past years is caused by the fact that we have a heavy pollution of our oceans and our river, which is going to impact on our food chain. See on the right, a piece of plastic eaten by phytoplankton. And as you can see here on the picture in the center, I started to introduce some t-shirts because the reaction of the population that it's one of the driver of the last decisions, policy decision was by people that reacted regarding this pollution pre-COVID, I have to say, saying no more plastics. But no more plastic, what happens? That effectively the legislature in different countries decided to follow this reaction, banning polypropylene, banning polyethylene for some application, banning polystyrene for other applications, because these were recognized as the bad boys. And there is an entire industry suffering for this. But what's the function of packaging? That's the point I want to highlight all the time. Maybe it's redundant, but we have to think about that the packaging was created to preserve food. The entire history of humanity was characterized by the fact that people needed container for their food. Imagine cups on clay to preserve wine and oil during the Roman Empire for the entire history of humanity. We started folding in leaves, and then we landed to put meat in plastic container like these ones. These are two packages of salami that I brought with me before the COVID to do a picnic with my kids. And the right one was kept closed and the left one was open with the same thermal history. The left one at the end was oxidized and the right one is perfectly good. The point is that I have amazing food with a little amount of preservatives that is preserved on its quality just because the packaging. This is healthy food all the time. But the impact of wasting food is not about money, but is also about on CO2 emission. Then we need a whole view when we think about food wasting. For example, look at meat. If we waste in the US 70 million tons of, some 70 million tons of meat, what we have into CO2, 130 millions wasted. It's the same for fish and the other food. So I think we can conclude that the food preserving is fundamental, especially when we have a growing population that by 2050 is going to be 9 billion people that we have to feed these people. And of course, packaging, like every other object that we can create, can be over-packaged. Then we can pick a piece of chocolate, put in it aluminum foil, then in a plastic foil with a lot of colorant and everything in a box. This is for sure, it's an excess of packaging. But if we under-design packaging, we have an excess of product waste, which is not proportional, but it's completely curved symmetric. Of course, we have to find the optimal packaging. Anyhow, food saving is mandatory and passed through packaging. But what about textile? Can we ban textile? This is going to be the result. No more clothes. Can we reduce the use of clothes? Not always. But why Maurizio brings the highlight on textile and packaging, why Maurizio brings the comparison between packaging and textile. For the simple reason is that if we want to preserve food, then we need complicated packaging. It means that we mix a lot of materials. Imagine white bottles used to preserve milk. They contain titanium dioxide, they have as a UV interceptor, they have an interlayer with nylons, with carbon black as an oxygen barriers. This material is beautiful, but it's not mechanically recyclable, and it's a multi-material. But what about textile? Textile is immanently multi-material. You have a t-shirt which is not transparent because it contains some titanium dioxide to give opacity. Then you have pigments, dyes, and maybe your denim, they have some stretches. Then it contains some polyurethanes. And then you have cotton mixed with polyester because 100% cotton has some properties, and maybe mixed 50% with polyester is another properties. But this material, they cannot be recycled. Why? Because these contaminants impede the recyclability. But we go back on this continent and we see what's the situation right now. If you see, these materials are only energy recovered in incinerator or landfill. And what's the demonstration on macroscopical point of view is that in the countries where the landfill is banned or restricted, we do not have any significant increase on the recycling rate, but we have a huge increase in incineration. So this is the demonstration that in virtuous country, the virtuous member state of Europe, despite the huge effort of citizens and the infrastructure to recover as much as possible materials, at the end, burning wins. So let's dive now on PET, and we see some numbers, and someone repeated these and there, but I wanted to highlight the point that we are more than 80 million tons of PET produced globally. It means 10,000 Eiffel Tower on weight. That's huge amounts produced per year. But among these, only few fractions, such as colorless or pale blue bottles, are really recycled. And among of this, they go to a new bottle. But the major part of this material goes to what? To textile production. So the 14 million tons of mixed color bottles and packaging like plastic trays, what they go? They go to polyester fibers. If it's not incineration, like plastic trays. So we have a huge red bar on the bottom and very few green light. But if we remove the other materials from the polyester, we can produce something virgin. It's exactly what chemical recyclers do. We fall apart the polymer, breaking down on the constituents. It means the building blocks of the polymer. And doing this, because we remove the entanglement of the polymer chain, we remove the additives. And we obtain the building blocks. And the quality of the building blocks, compared to the feedstock, is the goodness of our process. The building blocks now are reused to produce virgin polyester. Then we can really upcycle the polyester, closing the loop. And then we can complete with the green bar on the bottom. But what we do exactly in green? In green, we use, to accelerate the reaction time, we use a microwave oven that we have invented and patented. And in 10 minutes, we depolymerize the material, which start grinded. This case can be bottles, but we see other material later. Then after the material is depolymerized, the mother liquid is separated from the liquid part and the solid part. The liquid part is MEG, one of the two monomers and goes to distillation, and then products. The other part in water process goes to crystallization, and we obtain pure terephthalic casing. But the point is that because we do the reaction of saponification, we produce table salt as a byproduct. But the table salt is used in electrolysis to produce the chemicals we need for the reaction and for the workup. So we do not need external feeding of chemicals. We need only energy and a little bit of water to do the entire job. We don't need extra chemicals. So we do not have blind spot. We don't have gray areas. The quality of the energy you provide to the system give you different level of sustainability. We worked with different feedstock, from packaging to textile. Here are some examples. The top picture are white bottles containing 5% titanium dioxide, interlayer, and blah, blah, blah. Then we have colored bottles, plastic trays. The third picture are textile. This is an extreme textile containing 20 to 30% of polyurethane, plus colorants and so on. We depolymerized in our reaction, and what we obtain, colorless PETs. These are, of course, before SSP. You see, they are completely free. I don't know the ratio among them because we took a mix of this and we went to polymerization. But we have a huge and consistent energy saving in terms of neurohuman energy, and minus 64% of CO2 emission compared to the monomer produced from fossil fuel. That's very important because we have to compare chemical recycling in terms of product. As we produce monomers, compare the monomers to oil. We work also with other material, for example, polycotton containing 40% of cotton. You see, this is the material before the reaction. You see the signal of cotton on the right. And after the reaction, then the monomers of polyester are recovered. We have cotton in our hands. And what's going on with this cotton? You see, it's completely free of polyester. Then the cotton itself is suitable to produce rayon viscosa. So it's not a waste of the process, but it's a resource for someone else. This is the on textile. The on textile containing 25% of polyurethane and 5% of other colorants, pigments, and so on. It's horrible. You have to feel the smell of this material as a really strong soapy smell because of the industrial process. And now I want to show you the chemical result, compare the spec from oil. On the left, specification from oil, and on the right, you see the different material. You see the first one, which is the liquid, is in spec with oil, and you see the terephthalic acid on the bottom, despite different origin of the material from mixed colored bottle, plastic trays, white bottle, or PET, polyurethane, industrial. They are always the same results, always the same everywhere. The dots are always in the same point. Means that we have a stable product in spec with the material from oil. We work in a European project. That's why we are building a demo plant with the capacity of 1,000 tons per year. We do with the partner of European project that I always like to thank because we are really working hard all together. And the partners are, some are technical partners, some other are not technical partners. You recognize some of the brands. Also, not only from the packaging industry, but also from the textile industry. We were very happy with the results, and then we were very happy with the technical aspects, but we wanted to open to other brands that we work together. Then we got the endorsement from the other brands because we opened an industrial advisory board where we share information, and when they give us feedback and they give us information on how to implement this technology in the current value chain. We put together around the table the brands from the packaging industry and also from the textile industry, also from the home care industry. Again, I wanted to stress this point. Basing on the result, on the experimental results, we have this saving in terms of energy and in terms of CO2. Of course, in this counts, we comprehended avoiding the burning of the material as end of life. And the CO2 resulting from the emission in atmosphere for burning polyester is removed from this calculation. And we have minus 64%. I'm very proud to share with everybody the fact that in December 2018, we won the Innovation Radar Prize as Best Innovation of Europe. I think I went fast enough. Thank you very much for your attention.